Hey ladies and gentlemen, welcome to another session of Tech in 10 with Sin. I'm representing SynHardware.com, and today we're going to learn about one part of the motherboard in layman's terms, and that part is the voltage regulator module right here. Usually it's hidden underneath a heatsink, and the heatsink can always be removed by taking off the screws, but if you have a board that I've reviewed, there's no need to do it really because I'm doing it for you. And I don't want you to damage your board with the screwdriver or anything. I've been doing this for a long time and I've yet to kill a board like that. However, I've been doing this for an extremely long period of time. So underneath here we have what's being cooled down by this gigantic heatsink. Well, it's not that gigantic, but it's pretty big. Are these power stages. And in a normal motherboard, you don't really have power stages like this. This is an all-in-one power stage. Usually this is made up of a MOSFET, two MOSFETs and a driver. So usually you'll see two of these little things, two MOSFETs like this, but they don't look like this. This is old style MOSFET, and a tiny little driver that's like this big. Really tiny stuff. But these three chips would make up one of these chips, and they still do, and many motherboard manufacturers use them. If you have like a Z77X-UD board, like a UD3H or UD5H, or even a G1 Sniper series, from Z77 on Gigabyte, then you're going to see a four piece. You're going to have two low side MOSFETs and a driver. However, you're not going to have this type because this is a really crappy type of MOSFET. This is called a deep pack MOSFET, and they're not good for switch mode power supplies such as on a motherboard voltage regulator module. Okay, so let's get started. I'm going to leave this board here for reference so you can look at it, but I'm going to be doing everything on this dry erase board right here. Alright, so what is a VRM? Right? What is it? A VRM? VRM stands for voltage regulator module. Alright? Voltage regulator module. In real life, no one uses the M. They're just going to call it the voltage regulator. On a motherboard for the power supply for the CPU, which are these phases right here, actually in this case there's 6 for CPU V-core. 1, 2, 3, 4, 5, 6. Those 6 plus the capacitors, plus these input capacitors, these output capacitors, these inductors, these power stages, the power pin, and the CPU all have something to do. As well as one very important chip called the PWM, which is right here. It has a little yellow dot on it. I don't know if you can see it. It's right there. Right there. That's called the PWM. The PWM is the master control chip. So you have a PWM, and that's called a pulse width modulator. But it's the master control chip. I actually have one here from another board, and it's about this big. This is about the same exact size that it is on this motherboard. Then you're going to have drivers, alright, and or doublers. So I'm going to do doublers with a slash. Alright, and this little IC right here, this is a one input from the PWM can go here, and then this little driver IC will output 2 sets of driver signals. Alright? Well, I'll actually draw this in a better way because I'm actually going to do this right now with these components, and I'm going to show you what like a voltage regulator phase is made up of. Alright? Just for quick thinking. Alright? So this is the PWM. And this is the driver and doubler. It drives the MOSFETs and or doubles the signal, right? So this is just one phase, and then this little chip will make it 2 phases. However, that's not normal. Many times you just want single channel, single phase. But this can output to 2 phases, so this can go to 2 phases. Now this has integrated drivers, 2 of them, and the drivers connect to the MOSFETs. So let me see if I have sets of 2 here. Oh, I actually do. Alright. Well, actually this is a... yeah, we can use that. These are smaller MOSFETs, about the size you're going to see on a motherboard, and we're going to do 2 per phase. So here's 2 sets of MOSFETs. Alright, because this doubler is going to do 2. And the MOSFETs are what switches. They switch on and off because the whole point of a voltage regulator module is to take the power input from here, convert it down from 12 volts to 1.2 volts, which is the stock voltage for most Intel CPUs, and pulse current through each phase. So each of one of these 6 phases is going to be responsible for, in theory, 1/6 of the total output current, and it's going to pulse that current to the inductor from the MOSFETs. Now I'll explain that later. So you have the driver is connected to the gate of each MOSFET. So this is one phase, and this is your second phase with the driver chip right here. So now you have 2 phases. So this would be phase 1. This is the symbol for phase 1, and this will be symbol for phase 2. Alright, then in the MOSFETs you have a high side FET and a low side FET. High side FET and a low side FET. So I drew number 4. That's not right. A low side FET. The low side FET and the high side FET can be the same type of FET, and they both connect to the inductor, which I actually have inductors. One here, same as you saw in the ultra durable series. Then you have the inductor. Inductor stores energy and also makes those pulses a constant. A constant output is what your CPU uses. So here's another choke from like another board. Alright, so the high side FET is connected to the inductor, and so is the low side FET. However, only one of the two is on at a given time. Alright, so basically when the phase is on, the high side FET is on and the low side FET is off. And when this high side FET is off, this low side FET is on, and this high side FET is off. That's because each phase is only on 1/nth of the cycle, and if your nth number is the number of true phases from the PWM. So these 2 phases would in reality probably be on at the same time, or may vary because of the doubler. The doubler also cuts the switching frequency in half, so this could be maximum 1000 kilohertz, and this would only be 500 kilohertz at the MOSFET. So that's not a good thing about the driver. I mean the doubler. However, a real driver, if you're just doing a single phase, then that'll be the same switching frequency before and after. Anyways, these 2 go to the CPU, and these 2 are connected on the same side. And so this will go to the CPU. Alright, and then you have a capacitor right here. This is an old style OSCON. And the capacitor's one leg will be connected here, and the other leg will be connected to the ground. Alright, also your low side FET is connected to the ground, right? Low side FET to ground, low side FET to ground, and your high side FETs are connected to a 8-pin connector, right? Alright, I don't know if you can make sense of that because it's kind of confusing. Basically, these switch on and off, and they commit power. Now I'll go more in depth about the power stage when it comes up. However, what you need to know is, let's say we have 6 phases, okay? 1, 2, actually 3 phases. So you have a total of 3 phases. These are direct, no doubling. Alright, so PWM. Go into your phases. This is phase 1, 2, and 3. Alright, and they all go into their own inductors right here. M for MOSFETs, I for inductor. All these inductors are connected on this end together, okay? And so out comes here as a constant voltage. Here you're pulsing. Here is constant. Now, so you're wondering what the heck is all this about? Well, let me show you how it works, alright? So this would be like a square. When the square is up, the high side FET is on. The low side FETs are only on when it's in the low end, alright? And so it's going like this, and then maybe starts again and goes like this. So between here and here is a cycle, okay? And then this would be the beginning of a second cycle. Yeah. So we go here, and then we turn on phase 2. And then phase 2 turns on at the same time again. And then this is phase 3. You see how the squares are not aligned exactly, right? That's because each phase is on when the other phases are off. They're not all on at the same time. That is because, number one, to conserve energy, and also the way a switch mode power supply works in this case. So this is phase 1, phase 2, and phase 3. So phase on is on, and all the other phases are off, or they should be off, and this might be starting to turn on. Phase 2 might be starting to turn on. When phase 2 is on, phase 1 is off, and phase 3 is off. When phase 3 is on, phase 1 and 2 are off, right? At any given amount of time, these are off, this is on. Any given amount of time, this is on, and these two should be off, blah, blah, blah. So basically that's how it works. The current coming from the PWM, not from the PWM, from the MOSFETs is pulse through each inductor. Inductors store current in a magnetic field, and that magnetic field is discharged out of the inductor, and all the inductors go together to combine the current. And the inductor can take a pulsing power and turn it into a constant on its way out. So if you took a digital multimeter and measured here, you're going to measure the switching frequency. If you measure right here on the inductor, you're going to measure the frequency of 60 Hertz, which is the fundamental frequency. Here you might measure 300 kilohertz, which is 300,000 times per second that the phases are switching on and off. That's the thing. They're switching on and off so quickly, that in any given cycle is much less than a second. All right, 100,000 times a second is 100 kilohertz. However, in modern PWMs, you're switching around 300,000 times per second on each phase. So that can give you a constant output and you would never know the difference. Higher switching frequency has its benefits but also its disadvantages. So every voltage regulator works at an optimum switching frequency. So let me remove my components here and talk about some of the benefits of more phases, because this is about the voltage regulator module and that's basically how it works. So if you have a six phase from the PWM, then that would mean that if you have a 6-phase PWM, then that would mean each phase is on 1/6 of the cycle. Okay? Does that make sense? 1/6 of the cycle. If you have a 7 or 8 phase, then they're on 7 or 8 of a cycle. So 1/8 of the cycle, 7-phase VRM would have each phase on. So let me show you something, okay? Since each phase is turning on and off at a separate time, there's something called ripple, and we need to reduce ripple because the MOSFETs are switching on and off. They're creating AC noise, right, at the switching node, which is where the high side FET, the low side FET, and the inductor meet. That's called the switching node, and that's where a lot of the ripple comes from. And what happens is when you increase phase count, you're increasing something called the interleaving effect. All right. So if I have a 6-phase VRM, true, okay, that means each phase is on 1/6 of the cycle. All right. Now this 1/6 of the cycle allows you to take the ripple frequency and multiply it by 6. Ripple frequency multiplied by 6 would make a higher ripple frequency, which would equal reduced ripple amplitude, which would result in reduced ripple current. Alright, and this will work like this. Pretend ripple is a wave going up and down like this, right? Okay, and you want to make this V peak to peak. Ripple is measured in voltage peak to peak from here to here, okay? That's your ripple. You want to reduce that, okay? So when you increase the phase count, you're able to increase the ripple frequency. So you're increasing the rate at which this goes up and down. When you increase that rate, you also have the ability to reduce the amplitude, which is the distance from total bottom to total top. So total bottom, total top here, the distance is shorter than it is here because you've increased the frequency. When that happens, you're also reducing the ripple current because the ripple current is determined partly by the amplitude. And that out of the inductor will, by itself, just by having more phases, you can reduce it. So as you have more true phases, you can multiply this ripple frequency by that. So if you have 8 true phases, multiply by 8. If you only have 4, it's multiplied by 4. So if you have 4 true phases, we'll have more ripple than 6 or 8 true phases. Of course, this effect is not as big between 6 and 8 as it is between 4 and 6. Between 2 and 4, it's much greater than it is between 4 and 6, which is much greater than it is between 6 and 8. So it reduces. That's why you see most modern VRMs are based on 6 or 8 phase PWMs. And so let me talk about this doubling schemes, right? So let's say you have a 12 phase VRM, right? Alright? Well, how do you do that? Okay, most modern PWMs only come in 4, 6, or 8. There's one exception I know of, and that is the Volterra PWM, which is 10. But how the hell do you get the 12-phase VRMs? How the heck do you get the 16 and the 24? Alright? Alright? Now, I'm going to tell you how you do this by one word. Double. Double your pleasure, double your fun. Well, in reality, when doubling it does double the amount of components you have to use, which increases cost. It also can decrease a lot of stuff, like such as load across each phase and stuff like that. However, if you're using very good components, then there's no need and there should not be any voltage regulators above 6 or 8 phases. Remember, the interleaving effects are most desirable at 6 or 8 phases. However, there is an issue. There's only a couple manufacturers that make 8-phase PWMs, but there are a lot that make 6 and 4. So let's talk about the most basic. Well, I'll go to that scheme later. But let's try first to make a 12-phase VRM from a 6-phase PWM. So you have a 6-phase here, and it has 6 outputs. Alright? 6. Then how do you get 12? You go into little doublers, which will take one PWM input and output 2 more PWMs, right? And then by UC, you can go 6 to 12, okay? Very simple. You can also do this to go from 4 to 8, right? If you have 4, then you can go to 8. So how the heck do you get 24 phases if the maximum they make is 10, and no one makes 10? Most of the modern ones that you ever find on Motherboard are only going to be 6 or 8. So how the heck do you get 24? Well, there's one special doubler called the ISL. I think 6617. Alright? Now the 6617 is special, okay? It's just a simple 1 in, 2 out. However, what if you use 3 of them per phase, per channel on the PWM? Remember what I said, right? Switching frequency is divided in half, right? So it's 1/2 here, it's 1 here, 1/2 here, and 1/4 here after the second stage, right? So this doubles 1 phase into 2 and 2 into 4. That's, you can take 6, right? 6 and make it 24, okay? So you have a total of 18 of these little things. And so that's only 1, and then you take another 1 and you do the same thing. Now, phases need symmetry, so you always have to do the same thing to all the phases that are in use. Alright? So you cannot just do this to some of them and then just do 1 double per another one. Right? You cannot do that. You have to do the same thing per each PWM channel coming out of the PWM, because you need symmetry in the current and everything else. Okay? Now, doublers have some advantages, but however, you're still in that 6 phase going to 24. You only have 6 true phases, so your interleaving effect only goes true to 6. Right? Because only in each given cycle, each phase is only on 1/6 at a time. Or you're turning 4 on at a time, or you're changing your cycles. Alright, now here's a new type of doubler that's going to be used on the UP7. And this doubler will actually be able to change it. So the phase thing looks like this. So all the phases are out of phase with each other. However, that'll make it like in this one, it's like there's 4 separate 6-phase voltage regulators. In the 32 phase on the UP7, it is like 4 separate 8-phase regulators. Alright, now that's not going to help your ripple frequency really at all. But what it is going to do is going to decrease not the component cost. You can decrease the component cost, but when I've seen it done by Gigabyte, they never decrease component cost when they double. So your 12-phase VRM on a UD5H should have the exact same component quality as on a UD3H, right? Gigabyte doesn't do that, but I know other manufacturers that do. Let's take a look at another board though. Let's look at some inconsistencies, right? So let's say you only have ability to use a 6 + 1 phase PWM. Now what's this +1 about? Well, here you count 7, right? This is a 6 plus 2 phase. You don't have to use all your phases. Please understand this. So 6 phases are going to CPU V core, and what is this extra 1? This extra 1 is for QPI VTT. There are other voltage rails that need their own PWMs. So just QPI / VTT, as well as system agent. Right here, this is system agent, or this is system agent, and this is QPI VTT. These need their own pluses. So plus 1 can go to one of these, and then a separate PWM over here has to drive this one. So that's why they make PWMs with 2 rails. You cannot combine the rails, so you cannot make this 7. You cannot do that. So what if you have only a 6 plus 1 phase PWM and you want 8 phases? What do? Do you take 4 phases of these and you double them and have 2 go direct? Fuck no, you don't. What happens? So what do? You take 4 of them from a 6 phase PWM. So there's 1, 2, 3, 4, 5, 6. Plus 1. This plus 1 is going to QPI. So this is an ISL 6367. Okay, this is used on an ASRock Extreme 4 Z77. Alright, this has 8 phases, right? 8 phases is basically synonymous with this board. But is it 8 true phases? Heck no. Alright, so it's using this one is going to a doubling scheme, and you get 2 more out. That's 2. Another doubler. Another 2, so that makes 4. Another doubler. Another 2, 6. Another doubler. Another 2, 8. Now you have 8. 8. So what happens to these 2? They're not in use. So we can just erase them. Put them back to where they are. Basically tie them off to nothing, right? Put them in a stump. I don't know. So what does this mean? The ASRock Extreme 4 has 8 phases virtual. 4 true phases. That means the interleaving effect is crap. That is one reason you see so many output capacitors on the ASRock Extreme 4. Right? Do you understand how phase doubling can trick you? You think, oh, why shouldn't it be true? They have a lot of A-phase PWMs. Well, Interstill doesn't carry any. The only company right now that I know of that carries them that's used on motherboards is IR and Chill. Alright? And IR owns Chill. So Chill is part of IR. And no one's really using Chill anymore, they're just using IR. Right? So that's a little trick, how some motherboard manufacturers trick you. On these new Gigabyte boards where you see 8 phases, those are actually 8 true phases because they're using a new PWM. So here's a list of PWMs you might see in some of my reviews and what they are, okay? ISL 6367. 6 plus 1. IR, these are different companies. You see IR, ISL. ISL is Interstill, analog. IR is digital. Alright, very tricky, right? IR 3567 is a 6 plus 2 phase. IR 3563A is 8 plus 0 phase. CHL 3828 is a 7 plus 1 phase. This is the only PWM that can be made to run it, combine these rails into 8. However, on boards like the Maximus 5 Genie, it's only using 4 plus 1. Why? Because this extra voltage rail on this plus 1 is so much needed because it cuts the cost of a second PWM to run something else on the board. Do you understand that? You need a certain amount of outputs, right? You need V-core, you need DRAM, and X79 needs 2 times DRAM, okay? X79 requires 2 times DRAM, Z77 only requires 1. Then you need QPI / VTT, right? That needs 1 rail at least. Then you have system agent, which could be IMC, or VCCSA, and this is VCCIO. Okay, if you have an Asus board. And that's basically all that needs it. Oh, I forgot one big thing. On Z77 you also have iGPU, and that's what it's used for on Z77. So on the M5G they're using doublers for the iGPU as well as this. So they have 8 plus 2 plus 2, or 8 plus 4, where they might double it or try to use more MOSFETs. Basically you're seeing what I'm getting at, right? A lot of them are doubled. There are not many true 8 phases in Z77. The Gigabyte boards are, because they're not using this one, they're using this one. That's Gigabyte, okay, right here. Then we also have some MSI boards using a UP, I think it's like a 1816A, and that's a 6 plus 2. And while these all are digital, this is analog, and this is analog, alright? There's also a Volterra VT1165 or 85, and that might be like 10 phases. However, that cannot be used for modern motherboards because it is not VRD12 certified. I don't know if Volterra is working on new ones. TI actually has some very nice digital PWMs, but they're very expensive. Alright, so you're seeing what I'm getting at, right? You need more PWMs if you're only using 8 phases true for any of them. However, you can get away with using 4 and doubling it to 8. No one really notices except for me. Performance will be worse than if you're using 8 true phases, but that's what you get, right? There are a lot of haters out there who love Asus to the bone, and they're just idiots. Because Asus is going to start tricking them unless someone calls them out on it. ASRock is already doing it. I called Gigabyte out on it, and they fixed it all up. I'm calling Asus out on it, so they fix it up, and I'm called ASRock out on it, but ASRock's not a good enough company to fix anything. So that's our addition here. We're talking about the voltage regulators, doubling, and PWM schemes. If you have any questions or comments, please let me know.